thanks everyone for coming. Professor Sergey Foss and Heriot-Watt and Rotten Universities here to give us two talks. One quite topical talk, well, sort of an hour long of two talks divided up. The first one quite topical on ergodicity of stress release point processes, seismic model with aftershocks. And the second talk, which is given the really nice sunny day today, random walks in Poisson rain being a bit less topical.
Thank you. So I would like to give, I guess, I would like to give two 25-minute talks. So with 5 minutes for break, so if somebody is tired, he or she may leave after 25 minutes. Okay, my first, so there are both topics that relate to Poisson process, and the first one is stress with stress release seismic model with aftershocks. And the second one I will speak about Poisson random walk in Poisson rain. This is a joint paper with Pierre Brémaux and to appear in Markov process and related fields. So I will start with three models. One model is a stress relief model, the other model is the model of aftershocks, and the third model will be a combination of these two. And then I will come to this model, and on the second blackboard I formulate our results. So I will start with the first model, is stress release model. And this is known in the seismic as follows. So I will give you very simple observation. So we have, say, a Poisson process with intensity 1 on a positive in the positive quadrant. And you start with the following. You consider the following dynamics. I will write down first of all function. The function lambda of t is exponent of x naught plus ct minus sum of from 1 to n of t zi. It's plus here. And so, yes, where c is a positive constant, and zi IID, non-negative IID, and they are independent of a Poisson process. So we have two randomness. One is given by Poisson process, and the other one by positive random variables. What is going on? So we start with this function, so exponent to the power x naught, and start to draw this function, which is actually the stochastic intensity of the process under consideration. Our process is a function of these IID random variables and of this Poisson process. So we draw this function, exponent, we draw the function e to the power x naught, so e to the power x naught plus ct, till the first moment when we find a point of this Poisson process behind, yeah? Then we drop down by the level z1.
Below.
Huh?
Below.
Below, yeah, find a point below. Then we drop by z1. Then we continue. So then we start with the process x, we consider the process minus z1, this one, till the next moment when we find a new point, and drop down. Yes, and so this is a process which is called stress release model. And axis, the x of t is this process with this stochastic intensity. It takes values between minus and plus infinity. And so clearly, so if x is very low, it's difficult to find point behind. And so it takes more time to grow up, but because of growth is exponential, eventually you get it. And so it's a model is interesting model. It's known, so it was discussed in many papers and so it's in many papers by seismologists and then by mathematicians. And what is good, if you think about this model, it's a safe, self-stabilizing, because without any assumptions, this model is stabilized and converges to the stationary regime. Yeah, because when you're very far away, you drop down and so on and so on. You have this picture, and so without the result is this is stable.
So Sergey, what is the process you're talking about? Is it x of t?
X of t.
What is x of t?
X of t is a process
Lambda of t.
with stochastic intensity lambda of t.
So that is defined by a martingale formula.
Yeah, martingale formula, yeah, conditioned on that. You have to introduce the martingale, but it's
Yeah.
yes, yeah, you can do it immediately. So but you can do it step by step.
Yeah, but what is the martingale? So what is the martingale? It's x of t minus what is? So you have a compensator for x of t.
Whatever, yes, no need to do it. I'm doing it a sample pass, it's clear what I'm doing. I don't want
Clear
to.
to me.
You have Poisson process.
Okay.
You draw this picture.
What is this picture you're doing?
You draw exponent x naught plus ct. Till the moment when you find point below. You jump by that one. You continue. Till you find another point below. That's it.
Sorry, is ZT independent of the Poisson process?
That I said.
Yeah.
You have two independent random environments. That's it.
But
What's
if
the
Z,
other
if
environment?
Z is small,
What is the other environment?
They are IID positive random errors. I forgot to say expectation of Z is fine. The only constant. So
but sorry,
No, sorry. Again, you didn't say what x of t
Yeah,
is.
exactly.
Is it a point process that counts
Mhm.
something or what? You forgot to say that.
Yes.
okay, I would like to say it's a point process exactly with the stochastic intensity lambda of t.
So x of t is a
okay.
point process.
Yes.
Ah, you didn't say. I thought x of t. That's why I'm asking. I thought.
X of t is a point process. You find the x of t is a point here. First point, second point is here, and so on. Thank you very much for
So,
the
like,
process.
so what is the compensator then of x of t? So can we say that the integral from 0 to 0 of lambda of s ds compensates x of t? But this difference is a martingale?
Okay, I would like not to go further into this direction. So I would. I think it's the sample pass analysis is clear. Otherwise, I will spend a whole hour with this. You know.
So
I would
again,
Ah.
you're counting the number of points
Yes.
below this intensity.
Yes, that's it.
Of this point.
Yes,
That's
exactly.
The picture.
The
That's
picture, yeah. So it count number of points below this. We find it here and there. But you might think about the process lambda of t itself.
Yes.
If you like to see, it's like, and then you may forget about point process. It's just this function.
but,
It's symmetric stuff.
but sorry, if this Z or I are small enough, then it is possible to go to plus infinity for this function.
No.
Because it's not clear. You come in negative direction.
Okay, so it should be positive. If you are here, you assume the size is smaller, then you find more points here. Below and you jump more. So it's always stable. So it's very interesting situation. This model, if you think about this, it's always stable without any assumption. And you may think about this. You may speak about stochastic intensity.
Yeah, but that would make it mathematically precise. That's what I'm trying to understand.
What?
I forget about point process. Look at this function, that's it.
You're just looking at the random function lambda of t.
Yeah, but in other words, it's point process with this intensity, lambda of t. It's equivalent.
I don't think it's the intensity of the point process, it's of stochastic.
Okay.
No. It's very different to say intensity and stochastic intensity, because stochastic intensity is a conditional object given the path signal.
Yes.
So it's very so the intensity.
Given these values up to time t, lambda of t gives you stochastic intensity.
Stochastic, yeah. So
This was a stochastic
so
intensity.
therefore, x of t minus the integral from 0 to t lambda sts is a martingale.
Yes.
Okay.
So given x naught and uptime t, n of t, number, yes, and given z of t, we get lambda of t stochastic intensity at time t. But if you don't like Poisson process, just do this.
Stochastic intensity is not a very well-known object. That's why I'm just trying to get you to say the definition.
Okay, thank you.
So we understand what it is.
Thank you. So, but anyway, this process is stable over yes. And so, and you may put some generalizations on that, and then you get the following. What can you assume? You may assume this function to be, for instance, this random variables to be dependent, to put some more stationary structure, and this is depend on the height, whatever, and so using some good generalizations. But anyway, but there is a paper by Untitled from 2004 where he proved this stability of this result under some more general assumptions. And in particular, instead of function exponent, you may consider any function. Say here we may replace function e to the power of x by any function phi of x, which is such that phi it is monotone. Phi of minus infinity is 0, and phi of infinity is infinity. So you may do the same analysis by if you replace exponential function by any further function. Okay, and then the other model is a model of the Hawkes aftershock model, Hawkes branching process. HAWKES, it's a name, Hawkes process. And with stochastic intensity, again, you have a function lambda of t. You use the same type of structure. You consider any function nu of t and add the integral from 0 to t, h of t minus s, h of ds. And so, sorry, it shouldn't be h, should be n of ds. So again, you have a point process, and you have the following picture. So you start from some function, say nu of t. Nu of t is of any non-negative function, which is integrable. So integral from 0 to infinity, nu of t dt is finite. It's a deterministic function. H of t is an deterministic function. And what do we know about of t? Yes, and people in this epidemics, they call it h of t is called a fertility function. And this type of model is called epidemic type aftershock model, and it's present in some literature. And in particular, Daly and Very Jones, in their book in second edition of their book from 2003, are also doing this. And so study this, and so h is another function, non-negative. And one may assume that h is for its increasing function. Oh, sorry. So sorry, h so decrease h may be based as a decreasing function in t, and so the result is known. In this situation, and then the process with this intensity of this type dies out, so that the process goes to 0. People say dies out if the function h of t is integrable. Is an integrable function, so you may have some number of jumps up, so you may down and so on, but eventually this function goes down. And
Is it, sorry, what is it, n
is again, you play the same game. You draw this picture. You have Poisson process, and you have a jump up. At the first time, when you meet point under this curve, you have a jump up of size h of t, h of 0. And then if at time t you have 1 point, you add h of 0 because s is 0. And then it starts to decrease and so on and so on. And this model describes the aftershock situation, and so then the third, therefore the model which mixed these earthquakes, whatever model, and the model's aftershocks was proposed by the mixing stuff was proposed by Schoenberg and Bolt in 2000, and it was published in American Seismological Bulletin. Actually, Schoenberg is a grandson of Schoenberg, of a famous composer Schoenberg. And they said, let's consider a model with the following intensity, which is e to the power x naught plus ct minus sum from 1 n of t zi plus put y naught e minus alpha t plus integral from 0. I put here coefficient k, integral from 0 to t e minus alpha t minus x n of ds. So essentially this a function is this, say we have a function. Here we have initial function nu of t is yes this one. And so in this particular situation we have so phi of this function phi of x is still e to the power of x, and this function h of t is just e minus alpha t times k. That's it. So exponential functions both situations. So in this particular content.
I'm sorry, but I think you should make lambda of t left continuous. So n of t should be n of t minus on top of the summation there. But of course it doesn't matter. But that's anyway.
That's method. Okay. So in this situation, I would say, what do we get? You start. I prefer the following model. You consider Poisson process on the positive, say on the positive half plane. I will put point here. Here I put point y naught. Here I put point phi of e to the power x naught. And so we start with the following. We draw this function and we draw this function till the first moment when we meet. So when we meet a point in the union of these two regions between these points and this point. This is a function y naught e minus the alpha t, and this is a function e to the power x naught plus ct. When we meet this point, first point, this jumps down to level by level z1, and this element increases by level h of 0. And so we consider, so this jump down, so we get the situation, but this increases and this decreases. Each time we have this situation. So this is this represents the main. This part represents the main earthquake shocks, and this represents aftershocks, which give you secondary shocks of this type. So this model was proposed by these two people, and essentially, so we want. So this is the model, and so we've done. So Pierre and I. We just analyze this model, but in a slightly more general settings when we consider function phi more general function. So we analyze a model with this type of and plus second form is this of this type. So we have this process, and we want to analyze how does it behave. In this situation, so what do we have? Neither this lambda, neither any of these sums make is Markovian. But if we denote by this element by x of t, this argument of function phi, and denote by this by y of t, you get a two-dimensional Markov process, which is time homogeneous, which is continuous in time. And then we may analyze this Markov process, and the only stuff we've done, we consider ergodicity or stability analysis of this process. And so what can we say? What can we say? That here are the results. Here are the results. Result 1 is, so what can we say? We have a decrease rate minus alpha, here is t minus alpha, t minus s. A k is a multiplier. I'm sorry, it should be k times h of x. So we multiply coefficient, and this coefficient is, if you look in this situation, so the process dies out if this integral is finite. It means I'm sorry. This is a mistake. The integral has to be less than 1. I'm sorry. So here, only in this situation, the addition is smaller than 1. This is wrong. So if you represent this result, so the result is the condition k over alpha, in this particular case, which corresponds to this, is less than 1, is necessary for stability, for ergodicity or for stability, whatever, for stability, for stabilization of this process. Second condition is, if there is a second result is, if there exists stability, and if lambda, lambda hat is the expectation in the stationary situation of the process n of t, how many points do we have? Okay, I will put minus n of t minus 1 within unit of time.
I thought that n of t was a Poisson process.
Poisson process, yeah. N of t, no, it's not. It's a Poisson process with intensity lambda of t.
Ah, so then it is important.
It's a Poisson process in terms of.
That's why I was insisting on that.
Yeah, and so this one. Then with necessity, what do we get? if you look here, it's obvious result, obvious result. This is an increase rate. This increase rate. This is a decrease rate. In the average, if you use like Watt formula, you can get immediately that lambda of t, lambda times expectation of z, lambda hat has to be equal c over expectation of any of random variable z. So it immediately gives you the result.
So did you say that n of t is a point process with stochastic intensity
Lambda of t, yeah.
What is x of t then? I thought that x of t was the point process that has intensity, stochastic intensity lambda of t. And because we need it to be predictable, that's why I suggested
Here it was x of t.
Yeah.
Here we count only points here.
So in this part of the blackboard, that's x of t is equal to n of t.
Yes. But when you add up both of them, we get points between these two lines. And x of t is on yes. Only here.
But as I understand, you have no points of your Poisson process under this curve.
I see. So you change.
I count all these points. Yeah, you're right. You're right.
Okay. So the x of t that you write below is not the same as the x of t above. Okay, I understand.
Okay. And then there is finally we analyze this process. So I have to we analyze this process and we get the following results. So that clearly, if you can see the xn and yn as at the level of x of t, or just before or just after the nth jump, simultaneous jump, is after, say, after nth jump position, jump. And then this process is positive recurrent. The process is positive recurrent in the following sense that in the following sense, what do we say about positive recurrence? Actually it's a Markov chain. Markov chain, which is positive recurrent. And the positive recurrence in the following sense, there exists, positive recurrence means the following. There exists a compact set. You remember the axis between minus, so compact set, say k, in the interval minus infinity times 0 infinity. It's a state space for x, it's a state space of y, such that for any x and y, tau xy of k is a minimum n bigger than 1, that xn yn is in k, given x0 y0 equals xy, is finite almost surely. The first time to hit this, first hitting time of this set is finite, it's first column, and the second condition should be that x supremum in all x and y from this k, expectation of total x, y of k, has to be finite. So mean return time has to be uniformly bounded. So this is a positive recurrence. So so if we have this condition, under this assumption, we get that in this case we have positive recurrence, and then we have to assume under some smoothness assumptions. If you so this alpha of k less than 1, so sorry, k of alpha less than 1 plus some smoothness assumptions on the distribution on z, and gives us Heriot ergodicity of both Markov chain and the same and of process x of t and y. It's basic stuff, so given that a positive recurrence, you prove these results.
Your point x0, y0 is from K also.
No, for any point. You have a compact set, you have state space. There is a compact set. For any point from outside, or from any point, the time to get to this point has to be finite.
Yes, but the second.
But if you start from inside, you not only the time, but its mean, its expectation has to be finite, and moreover uniformly at all points from the inside. So it's positive recurrence, and then some basic arithmetic, more or less standard, gives you this result. This is theorem 1 and theorem 2, and surprisingly, the proof of this result is very technical and requires a lot of arithmetic. So
it presumably implies existence of the invariant distribution.
so what? This one,
Yeah.
without any assumption.
Well, I don't know. 4. Does 4 imply?
Higher ergodicity means the following.
Yeah.
I have to say, for any initial value,
Yeah.
so there exists unique stationary distribution. Higher ergodicity means the following, I have to say. There exists unique measure. You may call it invariant, you call it invariant measure, or stationary distribution, or steady state distribution, such that for any initial value x0, there exists a convergence of distribution of this one to the stationary one in very strong sense, in the total variation norm.
And you probably also have estimations for tails of this invariant distribution.
No, you cannot get it. You need further assumptions on that.
But you,
On phi,
you
whatever.
use a Lyapunov function to
Lyapunov function. Yeah, you cannot get. You use only Lyapunov function correctly. Yeah.
Well,
You have to find right Lyapunov functions, but without any further assumptions on the growth of function phi, whatever, you cannot get any result. Exponent.
And at what rate does it go to the stationary?
I told you it depends on function phi.
I mean, can you write
At what rate what goes to what?
the
Distribution,
Yeah,
convergence rates.
function goes to the distribution?
Convergence rates. So yes, you cannot get. You have to speak about function phi.
Okay, can you write it in terms of function phi?
We have not done it, but it's doable. It's more or less standard. If you get the result, then the function gives you something. It's the technique. The rest is more or less routine. So how to you have convergence? Yes.
well, it presumably also depends on the initial point.
Yeah.
It,
So you cannot say that.
yeah. Okay. So, but the Lyapunov function, you know. No. It's a standard. In terms of test Lyapunov function, there is a standard techniques which tell you if you have negative drift, if you find a right Lyapunov function, if you have negative drift, and if a positive, then you get positive recurrence, whatever, and convergence rate. If the positive part of the drift has exponential moment, fine, uniform point, you will get exponential rate of convergence.
But what is it exactly?
So,
Exponential with a uniformly bounded exponent.
yes.
What is it?
Perhaps you would like an answer for the case where phi of x equals e to the x.
Exactly, like one example, concrete example. What is it?
Yes, I don't want to improvise now. We have not done it in our paper, but I would say it's a student work in this case. No, I can do it within. It will take me, but I can answer your question, but later. But
Sure.
I have not done it. It's more or less straightforward. So because we can. I just want to tell you this we use. It was not so easy to find a right Lyapunov function, but if I delete this, I would say the following. The right Lyapunov function is as follows. So we found that Lyapunov function L of x and y. We found it. It's R1 x plus R2 y if x is positive and r3x plus r2y if x is negative, where r1 is much bigger than r2, much bigger than r3, which is positive. So this type of Lyapunov function we can see.
For which phi? For the exponential.
No,
So I can take phi of x to be e to the e to the e to the e to the x.
yeah. It's universal Lyapunov function which works in this situation. And in terms of this increment, then you have to say about exponential moment. So yes, I have to write down what this means.
So you piece together piecewise linear functions, and you say that works.
That works universally for any function phi. It's maybe it's of interest itself. I think that the result itself may be not so interesting, but I think at least my co-author was excited by the fact that this model is of interest. That indeed this gives you he said that he was trying to convince me that in seismology this is a very interesting. So it's a good model because this jump which relates to this part represents the first quake size, and this gives you aftershocks.
So what would it mean in terms of seismology?
Seismology, I would
Activity of this process,
say
particularly Harris recurrence.
Harris recurrence.
You have to eventually, the problem is of a point process. So this result should be translated to a result on point process x of t or n of t, whatever you call it, and say that this point process, something will happen to it after a random time, which lots of aftershocks, something.
Yeah, distant future earthquakes.
Well,
Do not care about past ones.
No, but
should say something relatively practical. You know what I mean in terms of the point process.
Forget about past.
Let's say okay. Here's a thought. Let's say that x and y are transient, x comma y. What does it say about the point process? Physically, does the point process blow up or become thinner? What do you think?
no, what means transient? It means there may be yes.
Well, it's actually a good fact.
It's only one way. It goes to infinity.
Right. And it actually
You cannot go. It cannot. In this model, x cannot go to minus infinity.
can go maybe probably studying the Martin boundary in the transient case might give you things about that. Depending on where you go.
I think it's. I have another 15 minutes to present another model. I think.
On seismology?
No, different. I was ambitious. I wanted to present another model on Poisson rain. Again, there's other one. I will just start it maybe about it to say about random walk in Poisson rain. It will take me another. I think I have another 15 minutes. I will do this. So everybody, yes, okay. Yeah. The other model is like this one. Again, it relates to the very old model of greedy server. So we have greedy server. I started a long time ago, and this actually is the result from very old. So from 90s, and with some field extension. So assume that there exists a Poisson process here, or Poisson field of rate lambda in the positive quadrant. And assume there is a point here, which I call it a server. And assume that the server starts to move in this direction with the speed 1. And simultaneously points start to move down also with speed 1. Here there is only, at the moment, one randomness. And so these points are falling down with a constant speed on this line. So that's why, so this is called a Poisson ring.
It's in the quadrant.
It's a quadrant, yeah, the Poisson quadrant. And essentially this point, so if you put this, if you think about this, put a diagonal here. So this, at the beginning, if you start here, and the first point you meet, it should be under this diagonal region, yeah? Because this point is falling down, then if this falling earlier, then a server comes, they meet. So what then will happen? Assume they meet. Then the points are like stones, you know, you're a car driver, and you meet a stone there. You stop, and it takes you some time to move it out. Assume that, yes, it takes a time sigma 1 to move this point out.
If it falls on the car?
Huh?
If it falls on the car?
No, it's impossible.
You still have to move.
Then you continue further and you meet the next point. Then which points actually will be next? I would say the following. No need to consider Poisson ring. Instead of that, I will do the following. I will say that my car is going in the diagonal, and when I meet the first point below, again like before, I stay there for the time sigma 1. Then again continue under 45 degrees. When I find a first point in this, next point in this area, somewhere here, say below, I move sigma 2 and so on and so on. Is the model clear?
And sigma can take value
Sigma 1 is a positive.
Sigma can take value infinity as well?
No.
Also it can not fall on you.
It's fine. It's fine. Yeah. So the question is, so but this is.
But they are random. So sigmas are random.
No, I didn't say this at the moment. No.
It
At the moment. So okay. So first, so again, now there's a new randoms may come. Sigmas may be either constant or random. It doesn't matter. And the only assumption I will have, the first assumption is, assume the sum from 1 to n sigma I, denoted by sigma n. We assume that sigma n over n tends to almost surely to some constant, say d, which is between 0 and infinity. Okay. And so, what can you say about this situation? And actually, there is a very, I think it was diploma result by Irina Kurkova a long time ago. I think it was 96 or 97, the paper, or maybe 96, Kurkova, a student of Malosh Vinchkov. And I think she proved the following. In the situation when sigma I have exponential distribution, this parameter, I think should be 1 over d, yeah? And if sigma i's are independent of a Poisson process, I use this notion for independence, then one can show the following result. First, let me denote by x of t position of a server at time t. Where is server time t on this line? Denote by x, so then x of x of n. So tn is a time of a completion of nth service. Yes? And then a position at time t, x of t, n is easily tn. So x, so then tn is x of tn plus sn. Time for work and time for, yes, okay. So anyway, and so xn, and this is just xn. You know this by xn. Where you are after n service. And so Kurkov proved the following result, that x of t is equivalent to 1 over lambda d logarithm. So it still goes to infinity by with logarithmic speed rate. Okay? still, but in a very particular case. And actually, it's I think about 5 pages, I don't know, of direct calculation basing some Chebyshev inequality, whatever stuff. And so one can ask, how crucial is this fact? Yes, exponential, whatever. No, it's not. It's to get this result, and the answer is no. It's not crucial, and in general, one can get the following result. So yes, one can get the result. Let me try to formulate.
Poisson is crucial.
Poisson is crucial. One can do it under general, but it requires much more. It involves so much of energy. But here it's almost free. You can use up more some nice property of Poisson process to get the following result. That actually, so if we assume only the sigmas, are independent of Poisson process, we have that Sn over n converge almost surely to constant t. Then again we have this result. The results are that xn looks 1 over lambda d logarithm n, and x of t is also equivalent to 1 over lambda d logarithm t. In discrete and continuous time, we have this asymptotic. So in any case, you have only low of large numbers, but you have still some drift to infinity. Xn is not bounded. Xt is not bounded. And moreover, essentially, one can prove a stronger result, that x of t minus 1 over ld logarithm t converge weakly to the proper random variable. It's very nice result. I think it's good. Then one can continue and ask the following question. One can continue and ask the following question. What one can expect if we replace this assumption by a slightly broader assumption? Assume that instead that we have something like this. Sn over n to the power of alpha converges almost surely to d, where alpha is now any function, any parameter between 0 and infinity. So alpha equals 1 means that yes, it's some memoryless property, some sense of a server. Server doesn't works with a constant speed in time. Alpha is bigger than 1 means that it requires more and more time. Server becomes tired. And alpha is less than 1 means that it's speeding up its service. It becomes more qualified.
You don't assume that sigmas are stationary.
No.
They may vary. Well, then you can know the velocity.
Yeah. No any assumption. The only assumption is a law of large numbers, strong law of large numbers. And moreover, I will not speak, but you can replace power functions by class of increasing functions.
In fact, it must be dependent to get something.
Yeah, maybe. Then the question is, there must be the question, but assume this is, and assume in addition, we assume also independence. We assume also that this sigma n are independent of Poisson process.
The Poisson. Okay.
You want to make it dependent of Poisson?
No, I don't want.
You may do it later, yes, but okay, we assume this stuff. So what can you expect? And essentially the story is, so yes, if you look at the line, so there are, on the line you have 0 to infinity, it's powers of alpha. There are two special points, a half and 1. And essentially there are four regions. A region interval from 0 to a half. Then there is just a point a half. Then the region from a half exclusive and 1 inclusive. And the region from 1 to infinity. And they give different answers. And so, but I will present this, and in this situation, I will present these results, and you will see what is going on. And you will see. Actually, so I will put this, I will consider these two cases separately. But you will see that actually 1 is a part of this. I will present this first separately, and then you will see the following. If alpha is bigger than 1, then we know that lim xn, lim x of t is finite almost surely. It's clear. It's a boundary point. Power 1 is a boundary point. If you do it slower, you will never get infinity. Okay. Alpha is 1 is already here.
Yeah.
Then alpha between 1 and a half. So questions about model. If alpha between 1 and a half, then you get very interesting result that we say the following, that xn is equivalent to 1 over lambda d n to the power 1 minus alpha over 1 minus alpha, and x of t is equivalent to, I will put 1 over alpha lambda d to the power 1 over alpha, t to the power 1 over alpha minus 1 over again 1 minus alpha. And I would like to see that if you look here, compare these two results, you will see a difference. Actually, logarithm is the integral of power minus 1. This integral of power minus alpha. And you see that this is actually, you can put these two together to get similar result, but anyway, it's not a power increase, not logarithmic increase, an increase of integral type of a power between a half and 1. So, but in this case, if you look here, how did I get this result from this result? Because I use the following very simple observation, that x of t over t limit is the same as the x of tn over tn. And tn is embedded epochs. And here tn is x of tn, so I would say x of n over xn plus sn. So in this situation, if alpha is between a half and 1, sn, so xn is negligible. And so in this case, I would say that xn is negligible of xsn. Most of the time is the survey is spent with service, and minority of time is spent in walking. Then the simple situation when alpha is between a half and between 0 and a half, it's more complicated. What can we say? We can prove only the fact that xn over xn plus sn tends to 1, or x of t is equivalent t. So we can get result for x of t, but not for xn. So in this situation, when alpha is very small, the customer is, or server is always traveling. And the very much more difficult situation was when alpha is a half. And in this case, one can show that x of t, so x of n, is equivalent to some constant, I will call L minus root of n, and x of t is equivalent to the L plus over L minus, or L minus over L plus t, and where L plus minus are very, you will see this, d squared plus 8 over lambda over 2 plus minus d. So it's a constant, it's a solution to some quadratic equation, but anyway, in this situation, you will see that both working times and service times are equivalent in this very interesting situation. And so they're proportional, and the coefficient of proportionality is here, L minus over L plus. And this requires a lot of techniques, so the proof of this result is really tricky and very nice. I like it very much, but it's also very probabilistic. I finished in the list. I would say the following: there is a lot of interesting problems here, because here you speak just about a single, about a single server. But let me try to just to mention a few very interesting problems which may be really challenging. Assume that now we have a Poisson ray on the half line, and you start two servers which are moving in the same direction. What will do? So what is the speed and how do they behave? It's of interest. So actually they will overtake each other. It's like in Edinburgh we have two buses. Bus number 22, and so they scale every second minute. And if there are some passengers on the bus stop, the bus which is in front stops here, and the second one overtakes, and so on and so on. They are doing this.
Passengers are former stop.
Yeah. And so what is the behavior in this situation? But you move further. You consider 3 points.
Yeah.
What will happen? Then one can show easily the following will happen. Eventually, so they will overtake each other, but eventually two of them will speed up. They will leave the third one, which is the third one who knows. But these two will speed up much faster, and one of them will be much slower. What will happen with 4, with 5, and so what kind of models we will have in this situation? There is a variety of interesting problems. What is the speed? What are limit distribution, and so on. Finally, like in the particle system, assume we have infinitely many points with equal speed.
They will split in pairs.
Yeah.
If not,
No. With 4 it will be eventually will be very big block. They will be all 4 together. One possibility, but eventually. Yeah.
4 together.
Yeah.
I think you will have
There will be 4 together eventually.
tools of random sizes.
It's very interesting restriction. So eventually, say with 4, what will happen? Finally, to speed up, assume 3 of them are faster. This last is here. And then out of 3, 2 will speed up, and they leave the third one. Finally, the fourth one will approach the second one, and they will speed up, and they will get this 4.
When you're saying speed up, do you mean that they accelerate or they still move?
No. The two together have a higher speed.
yes. But why those two that are behind have higher speed than those two?
Because they're in the same environment. These people who are in the front cars, they meet only all news. And two who are behind.
Well, they have their own passengers.
Yes. But look, assume I pass here already. No. I think that they will touch them. Okay.
You think?
Yes. Okay. Let me finish. Yeah. Okay. And assume that you have like in particle, like in a particle situation. So we have you have a starting point. There is no only points. You have infinitely many these elements. Assume you start this evolution, falling down and go this direction. What will happen? Another model. Take a lattice. And
You will have probably an invariant on the process.
Yeah. What do we have? What is how many points? Whatever. So I will just add 1 minute more. Assume that we have a lattice in the positive quadrant, and assume that we may allow it to move only, and assume that there is a Poisson ray everywhere here in each segment. Poisson ray. You start here. You are allowed to go either right or up, east or north. And assume you have to go from here to here, from 0, 0 to n. You have a variety of stages. So you may think about last time. So assume that you may you investigate all possible directories. So you may think about the first time to get there, last time to get there. It like corresponds to first pass or last pass speculation. One model. Another model. Assume that 2 cars start simultaneously. And assume that at each this point they may use next direction, up and down, with equal probabilities.
Independently.
what might happen? So, but eventually you have to. So yes, you have yes, and assume that what the speed of them. So they will meet from time to time. They will cross the ways. Okay, so it's just I mentioned just few more, but there are more interesting problems of this type. Thank you.